Free fall is defined as a vertical, upward, or downward motion with only gravity acting on an object. This is a strict definition, bearing in mind that even friction, such as air friction, is neglected when solving free fall problems. Knowing that until now no such perfect vacuum exists, we can confidently say that the scenarios of free fall problems are ideal ones. We can derive the equations of motions used to solve free fall problems by recalling equations of motion used in the previous topic, horizontal motion with constant acceleration. So these are the equations 1.1, 1.2, 1.3, the one on the left column. In free fall equations, the one on the right column, we simply replace the acceleration variable A found in horizontal motion equations with the acceleration due to gravity g. So here in 1.1, in the previous lesson, A Tf minus T naught equals Vf minus V naught. A becomes G. So it is now G Tf minus T naught equals Vf minus V naught. This is now our free fall equation number 2.1. For the previous equation 1.2, 2a xf minus x naught equals vf naught squared equals vf squared minus vo squared. It is now 2g open parenthesis yf minus y naught equals vf squared minus vo squared. A becomes g. And here we also transformed the variable, the x variable, to vertical displacement y variable to consider motion along the vertical in the y-axis. So this is our second free fall equation, equation 2.2. Recall our third equation from the previous lesson. That was equation 1.3. xf minus x naught equals v naught tf minus t naught plus 1/2 a tf minus t naught squared. Then in our free fall equation, this will now become, the x will become y to consider the vertical motion, yf minus y naught. And then the a in the second term, in the right side of the equation, will now become g, 1/2 g tf minus t naught squared. And this is our third equation, 2.3. Here we have g is equal to negative 9.8 meter per second squared, or negative 32 feet per second squared. Negative because in our sign convention, we have chosen going down as negative. To clearly define our sign convention for this lesson, we have table 2.1. For variable g, direction of motion going up, the sign is still negative. And going down, the sign is also negative. And variable delta t, elapsed time, t final minus t naught, going up is positive and going down is also positive. Because time always moves forward, so elapsed time, delta t, is always positive. Variable v, or velocity, going up is positive and going down is negative. Variable y, or position, we have going up is positive and going down is negative. Moreover, it should be noted that for our first variable g, it is always negative because when an object is going down to the negative y in free fall, it speeds up. Thus, its acceleration vector is directed in the same direction as the motion, negative y. On the other hand, when an object is going up to the plus y, it slows down. Hence, its acceleration vector is pointed opposite to the direction of motion to the negative y. It should also be noted that we recall time sub 0 or time naught or t initial is always 0. Sample problem 2.1. From rest, you drop a 1 peso coin from the top of a building. Neglecting air friction, calculate its position, the position of the coin, and its velocity, the velocity of the coin, while freely falling after letter A, 1.5 second, letter B, 2.5 seconds, and letter C, 4 seconds. Note here, we'll be using G equals negative 9.8 meter per second squared. So you drop this coin on top of a building. Here is our sketch. For the given, initial position is when t sub 0 is equal to 0 and v sub 0 equals 0 and y sub 0 equals 0. Initial position. Then the moment the coin is released, after final time sub 1, after 1.5 second, we have a known v final 1 and a known yf sub 1. That's position 1. After 2.5 seconds, position 2, we also have the unknowns vf sub 2 and the position yf sub 2. And after 4 seconds, that's tf sub 3, the vf3 is unknown and the yf3 is unknown. So that's for position 3. To solve this, we first choose from among the free fall equations 2.1, 2.2, and 2.3 what to use to find the unknowns. Recall that we may use any of the equation as long as we have transposed that equation correctly. Again, we write all the equations, put a check on all the given variables, a question mark on the unknown, and drop or cancel all the variables with 0 values as follows. For equation 2.1, we rewrite it. It's G Tf minus T naught equals V final minus V initial. This is our 2.1. Equation 2.2, we have 2G Y final minus Y initial equals Vf squared minus Vo squared. And equation 2.3, we have Y final minus Y initial is equal to V naught T final minus T initial plus 1/2 G T final minus T initial squared. This is 2.3. Dropping now all the zeros in the derivation of free fall, actually T naught is equal to 0. So T naught is 0. T naught is 0. T naught is 0. And here in our problem, V naught is also 0 because this is dropped without effort. So V naught is 0 or V initial is 0. V initial is 0 in 2.2, V initial is 0 in 2.3, V initial is 0. Notice in 2.3, since V initial is 0, our first term now is 0. So equation 2.3, we only have one term on the right, the second term. For the unknowns, we are looking for the V final for all the positions 1, 2, 3. So 2.1 unknown V final, 2.2 unknown, 2.3 there's no V final. And of course, G is available. We check that one. That's a constant. That's negative 9.8 meter per second squared. And T final, we have all the T final for positions 1, 2, and 3. T final. T final. For Y final, it is also unknown for all the situations, all the positions. Y final. Y final is unknown. Y naught is 0 here. Initial position is 0. So I'm dropping this. All right, so our equations are now ready. For letter A, the question again is calculate the position of the 1 peso coin and velocity while falling freely after 1.5 seconds. So this is letter A. Position 1, at position 1, which is at 1.5 seconds, we are to solve for position YF1 and velocity VF1. So looking closely at our equations, we can see that for letter A, we are to solving for YF1 and VF1 at TF1 equals 1.5 seconds. We can actually use VF, the 2.1 equation to solve for VF1 because that's unknown in 2.1 equation and the rest are given. And we can use 2.3 equation 2.3 to solve for YF1. YF is unknown in 2.3 and the rest are given. Also the TF. We have the TF and we have G and we have TF. All right, so solving now for YF1. Get YF1 using 2.3. So YF1, I'm now placing the subscript. YF1 is equal to just the second term because the first term of 2.3, the right side of 2.3 is 0. So we only write the second term, 1/2 G TF squared. Substitute 1/2 G is negative 9.8 meters per second squared. And T final there is at 1.5 seconds and square. Using your calculator, you should get an answer of, for YF1, negative 11.025 meters, or you may say the coin is 11.025 below the starting point or below the initial position. That's why it is negative, because it is below our initial position. Getting now our VF1, we use 2.1. So here we can see that we have GTF equals VF. Okay. So get VF1 using 2.1. So that's GTF1 equals VF1. Substitute, G is negative 9.8 meters per second squared. TF1, we are at TF1 equals 1.5 seconds. That's our VF1. Using your calculator, you should get an answer of negative 14.7 For the unit second over second squared, that's meter per second, and that's a correct unit for velocity. Negative because the coin is falling downward. It is going down at time TF1 equals 1.5 seconds. So for letter B and C, for letter B, we get the same unknowns. We have to get the position and velocity at 2.5 seconds. And for letter C, we are to get again the position and velocity at 4 seconds. So in a similar way, using the same equation and the same process, for letter B, we get the YF2, position 2, and velocity VF2 at TF2 equals 2.5 seconds. Again, we use equation 2.3 to get YF2, position at 2.5 seconds. So here, YF2 equals 1 half GTF2 squared. So this is our equation 2.3. We substitute 1 half. The G is negative 9.8 meters per second squared. And here, the time now at TF2 position 2 is 2.5 seconds. Using your calculator, you should get an answer of negative 30.625 meters. For the unit, second squared over second squared, that's 1, or cancel. So we are left with meter. Or we can say that the coin is 30.625 meters below the starting point. To get now VF2, we again use our equation 2.1. So VF2 is equal to GTF2, substituting the constant G, negative 9.8 meters per second squared. And here, TF2 is at 2.5 seconds, position 2, equals VF2. Using your calculator, you should get an answer of negative 24.5 meters per second when you multiply negative 9.8 times 2.5. This is now the value for VF2. Or we can say here that after 2.5 seconds, the coin is traveling downward at 24.5 meters per second. For the position 3, we are to get the YF3, position 3, and velocity VF3 at 4 seconds. Doing the same using our equation 2.3 to get YF3, we have YF3 equals 1 half GTF3 squared. And so our 1 half, substitute the G, which is negative 9.8 meters per second squared. And this time, the third, for the third position, we have TF3 is 4 seconds, and square that. Using your calculator, execute 1 half or 0.5 times negative 9.8 times 4 times 4, that's 4 squared, so 16. You should get an answer of negative 78.4 meters. Now, for the unit, second squared over second squared, that cancels, or we have there 1, so we are left with meter. Lastly, to get our VF3, we again use 2.1. And then we substitute the given. For VF3 equals GTF3. G is negative 9.8 meters per second squared. TF3 now is 4 seconds. You use your calculator, you multiply negative 9.8 times 4, you should get an answer of negative 39.2 meters per second. So that's the meter per second is from second over second squared. So you're left with 1 second in the denominator, and you copy the numerator. So meter per second. That is our VF3. This means that the coin is falling downward at 39.2 meters per second after 4 seconds.